let's get into section 8.4, which is now beginning to actually talk about probability. And in these questions, it's a lot very similar to the questions we were asking before, but now we're going to be asking something like, what's the probability that an outcome happens given a particular sample space? So far we're kind of talking about, we're focused on how many outcomes are possible, and now we're going to actually start throwing out some potential things that could happen and wanting to know what's the chance that this could happen. And to gamblers, or whatever, these are really important, or gamers, or people who enjoy games of chance. And a lot of times, understanding the math behind it is crucial to understanding the game and actually being able to win. And I'm not a poker player or gambler or anything, but I still enjoy the math behind it. I think it is kind of fun and interesting because, like, without really delving into a lot of these concepts, it can seem like an insurmountable amount of math to really progress. But if we kind of build things up in a certain way, it can make something that seems remarkably complicated, like having a million possible options, and kind of grinding it into a simplified solution. But let's discuss some of the terms in 8.4. Also, I decided to skip 8.3 for our class because we're out of time, which the second part, which is on set union, set intersection, set complement, and basically set operations, which are actually quite important in the later chapters. But if you're interested more in probability and reading the rest of chapter 8, make sure you go back to 8.3, and there's part of it that I just skipped because this week's lecture is quite long as it is. I'm trying to get into the basics really, and not getting into the more advanced probability calculations, since we only have 1 week. Anyways, the first definition I want to talk about is what is an equiprobable space, or equiprobable, equiprobable, however you want to say it. But it says a sample space S is called equiprobable if and only if the simple events are equally likely to occur. And really what that's saying is that if I think about all the events in the event space, if they're all equally likely or equally probable, hence equiprobable, say that word 5 times fast, um, it's just a space where everything's likely. So for example, flipping a coin is considered an equiprobable space because there's two outcomes, heads, tails, each is equally likely. Well, actually, technically, with using a random US coin, it's actually not 50-50 because there's a slight weighting advantage to most coins. And this is something that to people who really look to extort or use gambling to their advantage would probably know, well, what's the chance you actually get heads? Or they're what are called weighted coins. Certain coins have a much higher chance, like, of getting heads than tails, or vice versa as well. But usually when we're solving these problems, like using coin flips or dice rolls, we're assuming that each outcome is equally likely or equiprobable, and that's just kind of what we mean in this case. Another definition from the book that I thought I'd mention is if S is an equiprobable space with n sample points or outcomes, then the probability of a simple event occurring is given by the probability is 1 divided by n. And all that's saying is, let's say that, like, in our equiprobable space of coin flips, we had two outcomes, right? Which were the outcomes. Um, sorry, let me write it out. The sample space is equal to heads or tails. Um, but basically, there's only two outcomes. I could think about one event A, as being the sample point H, and a sample point just means it's like a subset. It's one possible outcome in that event. A different event would be T if I flip tails. But basically, what it's saying is that the probability of getting this outcome is the number of events in the outcome divided by the number of events in the sample space. So 1 out of 2, right? 1 half, 50%. 50% heads, 50% tails. And again, assuming it's equiprobable, that always gives me this assumption that it's always 1 divided by the number of outcomes. Or say, for example, in a dice roll, a sample space of 1, 2, 3, a standard die of 6 sides, not dice come in all sorts of sides if you didn't know. Um, but basically, there's a 1/6 chance of getting a 1, 1/6 chance of getting a 2, so on and so forth, as a very basic property of equiprobable space. And in most questions, how it will be phrased is 4 fair coins are tossed. Fair kind of implies that it's equiprobable, or a fair die. But if it's not fair, that just implies that the probability is not 50-50 or 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. I think I said that the right amount of times. But anyways, if you get what I mean, that's kind of the idea behind that. And the final definition, this is kind of another super big key about probability, uh, which says that if S is a finite equiprobable space for an experiment E is an event, then the probability of E is given by PE is equal to PS1 plus PS2 plus PS3 dot dot dot, and so on. But what that's sort of saying is if I have a particular event, which is a combination of multiple different events, like say for example I'm rolling a die, and I want to know what's the event that I get, either a 1 or a 2. Um, Basically, I could think about that as the series of separate events, event that I roll a 1 and an event that I roll a 2 as separate events, where event 1 has 1/6 of a chance of occurring, event 2 has also 1/6 of a chance of occurring. If I add those together, P of the sample point 1 plus P of the sample point 2, what I would get is 2/6, which must be equal to the probability of this larger event consisting of multiple sample points 2/6, which is exactly the case in this situation. Or equivalently, we could say the probability of this event is equal to the number of elements in this event divided by the number of events in the sample space, where there's two objects in the sample space, two objects in the event space divided by 6 objects in the sample space. Or I could look at them individually. So either or, and both of these facts are useful for various properties of basic probability. But anyways, we'd come up with 2/6 as the total chance of rolling either a 1 or a 2, which again is kind of obvious, but we can apply these ideas in conjunction with all of our talks about permutations and combinations to solve more difficult and more complex problems. Problems that I'm sure you've seen before and are difficult for the average person to solve because a lot of times they don't really have a very good fundamental understanding of the fundamental counting principle, permutations, and combinations. But all of those ideas kind of put together, I think, make this a lot easier, which is why we're kind of following in this order. And I think the book does a good job about working through these problems in a sensible solution. So let's look at an example. And you can use all of the ideas together to help. Like you don't like another thing the book goes into is you don't necessarily have to solve a problem in one way. There's often multiple different approaches which could guide you to the correct answer, and that's kind of what I wanted to look at in these last few examples. But in example 10, it says 4 fair coins are tossed. How many outcomes are there? Write out the sample space, and is it equiprobable? Excuse me. So since we're using fair coins, yes, it should be equiprobable, since each outcome heads or tails is, fair. And if I keep flipping them, each of those outcomes is also fair, so the whole space should be fair. But we could kind of look at this um, by actually examining all the outcomes. And this is one way that I suggest getting started if you're trying to determine all the outcomes. But also, if I wanted to know how many outcomes are there and I didn't want to actually write out the sample space, I could just use a basic exponent. Since each coin toss has 2 options, and I'm repeating the experiment 4 times. So the number of outcomes should just be equal to 2 to the 4th power, right? Because if I think about the first coin flip, 2 options. Second coin flip, 2 options. Third coin flip, 2 options, 2 options. So really what that leaves me with is 2 times 2 times 2 times 2, which is going to be 16 total outcomes. And that's kind of a good thing to get started with, because if I'm trying to write out the sample space, I know how many things I'm looking for in this problem. And notice I'm not using a factorial because it's not like I'm repeating the thing. It's like it's being redrawn in the deck. When it's being redrawn, you're not reducing it by 1 each time like a factorial. So it's not really a permutation or a combination. But anyways, we could also write them all out using a sample space. So this sample space would consist of, well, obviously like what I would probably do is start with, well, it could be all heads. I could then have 3 heads and 1 tail, so it could be heads, 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 tails, heads, tails, heads, heads, heads. Oops, I want to keep this more organized. Heads, heads, tails, heads, but whatever. It doesn't have to be organized. I just generally like to organize my permutations. Um, if you know what I mean. And I'll make another column here because since it's 16, it should be 4 by 4, and then it could be um, heads, or sorry, I could start with tails and then follow up with heads. And I mean, there could be a different way I'm going to organize it, but I'm just going to sort of randomly organize it in the case of this because I've already started. But there's another sensible way you could list each one of these outcomes. What I would probably do is start off by saying, well, what if I started with heads, then what, and so on. But how I'm going to do it is I'm going to say, well, what are all the cases to which I could have 4 heads? What are all the cases I could have 3 heads? What are all the cases I could have 2 heads and so on? Or maybe it's easier to just move to all tails next. Like there's only one way of having all tails. There's only one way of having one head, so I could do heads, tails, 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 heads, tails, tails. I could have tails, tails, head, tails, and tails, 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 heads. And again, I could technically solve problems without having to do all this, but it's kind of helpful for if you're a perfectionist or a completionist to really understand every outcome that could happen. It helps later when we're thinking about probability. And that's the only way to have 3 tails, and then the remaining 6 should be the number of ways that I could have uh, 2 tails. And actually, notice each of those is also a combination. It's 4 choose 2, 4 choose 1, 4 choose 0, 4 choose 3, 4 choose 4, because I could, anyways, I don't want to get into that, but technically, part of this is Pascal's triangle in the triangle line of 1, 4, 6, 4, 1, which all cumulatively add up to 16. The total um, exponent. Anyways, I'm trying to not get off topic. And there's so many different connections with the numbers that are quite interesting here. But there's going to be 6 in 4 choose 2, which is like I could have tails, tails, heads, 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 tails, tails. I could have heads, tails, heads, tails, tails, heads, tails, heads, uh, tails, heads, heads, tails, or head, tails, tails, heads. And I believe those are all, well, I know that's all because I already knew the total number of outcomes, but it's a way of really knowing and checking yourself for the full sample space. And it's equiprobable because each one of the coin flips was 50-50. So, each one of these outcomes is equally likely. Now we could focus on other problems because basically we know the number of events in the sample space and it's equiprobable. But next it says to determine the probability that all are tails. Well, notice that that's only one possibility. And since each of those 16 events are equally likely, basically there's only a 1 in 16 chance that this could happen because this would be our event, the probability that all are tails. There's only one element in that event. So if I take the probability of E occurring is equal to the number of elements in event E divided by the number of elements in sample space S. Sometimes the number of elements in the set is referred to as the cardinality of the set, just a mathematical term for that, which isn't usually, this notation is a little bit different, but basically that's totally fine. The number of events in E divided by the number of events in S, which is of course 1 out of 16. Or, this is a very basic facet of probability, but the whole equiprobable is an important thing because sometimes things are not equiprobable, and that complicates the probability a bit further. But anyways, we're left with a 1/16th chance of throwing 4 tails in a row. And if you run this experiment for yourself, there's also not a guarantee that if you run it 16 times, you're going to get that outcome because each time you run it, there's a 1/16th chance, or if we wanted to write that as a percentage as probabilities are commonly done, it's about a 6.2, or it's exactly a 6.25% chance of occurring. Now, if you run this event 16 times, there's a pretty good chance you're going to get this result, but it's not guaranteed. And there's a lot more math that goes into actually carrying out experiments. But if you run this experiment, say 1,000 times or 1,000,000 times, you're going to see that it will be about 6% of the time that you're going to get all tails. But you have to run it enough times due to what we refer to as variance. And in a very similar question, part C says determine the probability that at least 3 heads are tossed. Again, we could go back to our sample space and compare with the event space. So the event space, we want to know all of the different outcomes with 3 heads. So I'm going to go ahead and erase my circle on the tails. And so, like, my point is, if we have the full sample space, it's really easy to figure these out because we just can figure out how many options we have. But, we could have the case where we toss the heads first, or oops, that's 3 tails. Oops, my bad. But if you recall, as I was organizing them, that's kind of how I was organizing my results. Those 4 were the cases that I tossed 3 heads and 1 tails. But technically also it says at least 3 heads. There's also the chance that I could incur all 4 heads. So really this would be 4 choose 4 plus 4 choose 3 divided by 2 to the 4th, 16. And so there's some combination math that can all come together in this. And the book does a few examples of adding together the combinations. But I think it's a little bit more detailed than we need to get with this. For these problems, because I'm not going to give you a super impossible question on the final. But anyways, the event space is in red. I'll just be a little bit lazy here above, and that would consist of 5. So the probability of this event happening is 5 out of 16, or as a percentage, it's fairly decent chance, a little bit under 1/3. So 31.25% chance of getting at least 3 heads. And again, if you run the experiment 10, 20 times, you'll see that you'll definitely have quite a few situations where you toss 3 out of 4 heads. It's really not too bad. And it might be higher than you may have expected without actually running through the math behind this. Because I think a lot of people would guess that it's 1/4 since there's 4 coins and only 1 is tails. But notice that 1/4 is the case of exactly 3 heads and 1 tail. So the 1/4 logic that you might think is actually not wrong, but there's an additional chance of having 4 heads, which you might not factor in. And again, you could kind of think about this as 1/16 plus 4/16 because it's the chances of the individual outcomes. You could think of it as individually the outcomes of 3 heads and 4 heads, kind of separated, as it's kind of suggesting in the alternative form, probability of different events separated by what's the probability of all 4 heads or exactly 3 heads. So all those questions can seem similar, but common sense goes a long way, and building a sample space as well. But if the problem is too hard, like in example 11, it becomes a lot more difficult. In the next video, we'll get into that one.